Hi, I'm John Kroll, and for the past 5 years, I've been taking pictures of dog poop and drawing polygons on them and training object detection models to find the poop in images and measuring how well those detectors do on test and validation datasets. And then I uploaded it all to the internet and made it publicly available. And I wrote a paper on it and recently presented it at the WasteVision Workshop at WACV. And this is that presentation. In formal settings, we call this work ScatSpotter. It's a 76 gigabyte dataset of 4K resolution phone images. About a third of them actually contain dog poop because there's a focus on collecting hard negative examples, and we'll talk more about that later. Now recently, foundational models have gotten pretty good. But if you look at this in the zero-shot setting and you say take grounding dyno v2 and tell it to look for poop or animal feces or anything like that, the best you can do is around a 0.2 average precision. But if you take this dataset and tune a grounding dyno model on it, you get something that's just approaching good. I wouldn't say this problem's solved yet. There's still a little ways to go. To make this dataset accessible, I've released it under a permissive license and have experimented with both centralized and decentralized mechanisms of distribution, and I have a small study on that at the end. So to briefly overview, the main contributions are the dataset itself, the trained models, and the small distributional study. But before we get into that, you might be wondering, why did I start doing this? What's the motivation? Well, let me tell you a story. Back around 2019, I was walking my dogs in the park, letting them out playing, and it's leafy around. And all of a sudden I see that they're pooping. And fortunately, there's a bag station nearby where the city graciously provides bags that let you go pick it up. So I go to the bag station, and then I turn around, and then I'm like, I can't find the poop. Where is it? There's leaves everywhere. It's very cluttered. I can't see what's going on. And I thought to myself, man, if only I had a dataset of thousands of labeled images, I could train an object detection model and try to put it on a phone that would help me search around and find where the poop is. So I started taking images and building the dataset. Now, this isn't the only application of such a dataset. You could imagine smart glasses. An object detection model could warn you before you step in poop on a sidewalk. That might be useful. You might use it as a dataset to pre-train an object detection model to find feces of different species, to look for traces of animals and study the population of animals in an area. Maybe you want to put an object detection model in an autonomous robot to clean up poop in the backyard. That could be useful. And I think this is just an interesting problem of these small, tiny objects in these cluttered camouflage settings, and it's just an interesting benchmark data set. Now, when I talk to people and I describe to them what I've been doing, either they get it, they understand what the point is, they see the utility, they're on board, or they look at me kind of weird and they ask me, is that even hard? Just look at the poop, it's right there. Why are you even doing this, you weirdo? Well, I say to these people, can you find the poop in these images? Maybe you see one, maybe, but did you see all of them? Here they are. Let's do another example to drive home this point. These are cluttered scenes. The objects are small. They're basically camouflaged because they look very similar to the other clutter in the scenes. And here's the poop. So I hope that I've convinced you that this problem's hard, it's worth studying, and I want to talk to you about the dataset. So let's talk about the dataset. Earlier, I mentioned this before or after negative protocol. This is why a third of the images in the dataset contain poop and the rest don't. Because when I'm walking around and I see a poop, I will take a picture of it. And now, I usually carry my bags with me, so I'll take them out and I will clean it up. And then I'll take an after picture. This serves as a counterfactual. It's the same scene, but the poop has been cleaned up. Then, because areas where dogs poop might be correlated, I want to encode the idea that in most places that you look, you won't find poop. So nearby, I try to find maybe something that looks like poop or somewhere that could be useful as a negative, and I take an image of that. So you have this before poop is there, after poop has been cleaned up, and then negative, a nearby uncorrelated scene. And this is the basic way I've been taking images to build this data set. So, at a glance, this data set is biased towards my 3 dogs. I would walk them and they would poop, and I would pick it up and take pictures. But I would say maybe only 60% of the data is from my dogs, because as I'm walking around the city, usually with them, I will spot errant poops on the ground, and since I have my bags with me, I'll clean those up and take pictures of those too. So they've been added to the data set, and what we have right now is about 4,000 images that contain poop and around 11,000 images in total. As I said before, it's pretty big on disk because these are full resolution images, and they are mostly in urban environments. There's also an important point to make about the test set. When I started this project, I made a rule. I was not going to test on images that I took. I'll use my own images for validation, but I'm going to ask around for family, friends, people on the internet to send me images of dog poop. And for whatever reason, people didn't want to send me pictures of dog poop that often. So the test set only contains 121 images, but they are independently taken, so they're not my camera and they're not from me. And that's going to give us some degree of generalization, but it is a major limitation of the dataset right now, and I have a few plans to correct it, which I'll talk about later. So even though most of the images were taken by me, there is still quite a bit of variation in the dataset. The images were taken at all different times of the year, at all different times of day, in light and dark conditions. And while they were taken mostly in a single city, they were taken in various locations around that city. And there's a fairly even spread of coverage across time. On the bottom, I've computed ResNet 50 descriptors of all the images and laid them out in a UMAP embedding, and then picked points to give sort of a representative overview of what the dataset looks like. For annotations, I used the Label Me software. Originally, when I started doing this, I would just manually draw the polygons around the poop. But then models like SAM and SAM2 came out, and I started using those. Those helped a lot for the easy cases, but the hard cases I still had to manually draw. Similarly, as I got more and more data, I was able to start bootstrapping MaskR CNN models and using that to seed annotations for new collection cohorts. And that helped a lot, again, with the easy cases, but I'm still finding that the hard cases are difficult for these models, and a lot of the polygons are manually annotated still. And all of the polygons are manually reviewed. There's no automated labeling that hasn't been reviewed and then modified by a human, mainly me. Here, the middle image shows an overview of what all these polygons look like. And then on the right, an interesting property of the dataset is that most of the images that have poop actually contain more than one. A lot of times, my 2 dogs at the time would poop together, or I would go and there'd be collections of poop where different dogs like to poop together. So you get a lot of these different variations. It's not just a single poop in a single image. So because I've been training different models over time, dataset versioning is pretty important. And I've done different experiments on different versions of the dataset. So I have hashes of the dataset that are tagged for any experiment. So all my experiments are tied to specific tags of the dataset. For the splits of the dataset, validation splits are usually done by time. More details on this are in the paper. And as mentioned previously, the test set is small, but it's entirely independent from the images that I've collected. So for the baseline models, I started off this project using this vision transformer that was full resolution. It was originally for a different task, and I was just able to reuse the code for this. Didn't work very well, but I have a lot of experiments with that, so they're included in the appendix. The first model that started to do really well was a MaskR CNN tuned from ImageNet weights, and that's what I'm still using as my best polygon model right now. But recently, these foundational models are coming out. You have Dino V2 is the one that I've tested here. And I found when I used the 0-shot setting and I tried all sorts of different prompts for it, you got an AP of around 0.2. That was kind of disappointing because I thought this problem would be pretty easy for a foundational model. It turns out it can do okay. It does a lot better than the Mascara CNN if you tune it. So tuning it on this data set helps you get to about a 0.7 AP. Still, that leaves quite a bit of room for performance improvements, and I hope that more people looking at this problem and collecting more data will help get us to those better numbers. Also, because I'm interested in deploying this on a phone without cloud connections, I want it to run on the phone itself. I'm looking at mobile models, and I've been seeing how well the YOLO V9 is the one that I'm looking at here, and it does worse than the Mascara CNN. You get around a 0.4. It's sort of helpful, but it needs a lot of work, and next steps are going to be to distill the dyno weights into the YOLO weights. So here's examples of how it does on the grounding dyno model does on the test set. We have zero shot at the top. You can see that there's a lot of false positives, and then tuned, we do much, much better. But again, the test set's small, and I think the validation set's actually quite a bit more difficult than the test set. So looking at this, we can see that, again, the zero shot case has these clear false negatives, but when we tune the model, we start to hit them in these kind of pathological leafy conditions. But even with the tuned model, there's still some false negatives and false positives that need to be mitigated. For the YOLO models, as you might expect, there's a lot of false positives. That's just YOLO models tend to do that, but it does okay. This is what it looks like. But there's not too much to say about that. Foundational models do pretty good. The mobile models not quite as good, but you're getting there. I think we can do better on this problem, and I hope to. So, distribution. 76 gigabyte datasets don't distribute themselves. They don't host themselves. Fortunately, Hugging Face is very generous, and they give free tier users about 100 gigabytes of free space, which I am rapidly approaching as the dataset continues to grow. So because this is an independent project, I'm doing this on my own time, I'm interested in how can an independent researcher share their data without institutional support or relying on institutions more specifically. And decentralized mechanisms are an interesting way to do this. Specifically, I'm looking at BitTorrent and IPFS. And unsurprisingly, when you compare these to decentralized systems, they are much slower. But how much slower is what I've quantified here. They're at the point where you can use them. You can share your data using these distributed mechanisms. I have found that BitTorrent is more reliable if you have a tracker, because that lets you find peers to connect with and share the data between, whereas IPFS has an issue. If there's only one peer sharing the data, it can be pretty difficult for another person to actually find that person who's hosting the data. I have the data on a Raspberry Pi here, and sometimes people can't actually connect to my machine just due to the nature of how these distributed hash tables work. Something that really surprised me, though, was just how fast these centralized content distribution networks are. When you try to pull this, in this case, 43 gigabyte version of this data set down from Hugging Face, it takes 15 minutes, which blew my mind. It was faster than rsync between two centralized points. So that just having multiple streams from multiple upload sources apparently goes a very long way. So for future work, I want to get this thing on a phone. I want to get a good mobile object detector that can detect these objects at a point where it's useful, where it actually helps someone find a poop that they were having a hard time finding. And I want to get this application uploaded and make it free for everyone. I'm also interested in testing the more recent foundational models like Dino V3. Spoiler alert, I actually have been testing this since I came back from WACV, and I can't get it to tune better than Dino V2. I don't know what it is yet, but I'm still looking into that. I also need to expand the test dataset size. Something interesting that I found that someone on GitHub actually pointed me to. There is a bunch of poop datasets on RoboFlow. Now, the quality of these data sets and the licensing on these data sets is questionable. I'm not sure that I can include it with my data set, but we can certainly download them and test on them. So that's going to be a next step. If you want to contribute, if you go to the URL, there's instructions on the bottom of the page on how to, a Google form that lets you send me images, or an email that you can send them to. I'd love to get contributor images. If you want to benchmark new models and send me the results, or get a really good model working, that'd be super interesting. And we'll just throw this out there, if you have funding, I'd love to work on this project more full-time than I currently am. But with that being said, that's the presentation, and I just want to give a special thanks to my 3 main contributors, and thanks for listening.